welcome to the last lecture of the discrete math course. In this video, we're actually going to wrap a lot of content that we've learned together into one neat problem that we can now solve using all of the mathematics that we have discussed thus far. In fact, this example is a sophisticated version of the stamp problem. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below and make sure to click on that subscribe button. All right, let's take a look at this problem. How can you make $6.37 using just 5-cent and 8-cent stamps? What is the smallest and largest number of stamps you could use? First, we need a Diophantine equation. We will work in numbers of cents. So let's let X be the number of 5-cent stamps. And then we're going to let Y be the number of 8-cent stamps. Okay, we have here now that 5x plus 8y equals 637. So this is writing without using decimal places. We want everything to be integers. Now convert to a congruence and solve. So we have, for example, mod 8 or mod 5. We have 8y equals 637 mod 5, which can be reduced to 3y equals 2 mod 5. Okay, and this can be solved by adding 10 to the right side because 10 is a multiple of 5. And so 3y equals 12 mod 5. And because 3 and 5 are relatively prime, we can divide both sides by 3 to get y equals 4 mod 5. And that means that y equals 4 plus 5k for some integer k. That means k is an integer. So now we can plug that back into the original Diophantine equation. I need a little bit more room here. To get 5x plus 8y, but we know what y is, it's 4 plus 5k for any integer k, equals 637. Okay, so that means that x equals, in terms of k, it's 121 minus 8k, if you do the algebra there. This says that one way to make $6.37 is to take 121 of the 5-cent stamps and 4 of the 8-cent stamps. That's just if you pick k equals 0. To find the smallest and largest number of stamps, try different values of k. In fact, I have here a chart that can show you exactly what we can do with these values of k. And of course, it zoomed out. All right, there we go. So for example, if you plug in k equals -1, you get a y value of -1, which is not possible. You can't have negative 8-cent stamps. If k equals 0, we use 125 stamps. If k equals 1, we use 122 stamps. If k equals 2, we use 119 stamps. This is no surprise. Having the most stamps means we have as many 5-cent stamps as possible. And to get the smallest number of stamps would require that we have the least number of 5-cent stamps. To minimize the number of 5-cent stamps, we want to pick k so that 128, let me give myself a little bit of room here. And zoom in just a little bit more. There we go. We want to pick a k so that 121 minus 8k is as small as possible, but still positive. When k equals 15, we get that x is 1 and y is 79. Therefore, to make $6.37, you can use as few as 80 stamps, one 5-cent stamp and 79 8-cent stamps, or as many as 125 stamps, where we use 121 5-cent stamps and 4 8-cent stamps. Using this method, as long as you can solve linear congruences in one variable, you can solve linear Diophantine equations of two variables. There are times, though, that solving the linear congruence is a lot of work. For example, suppose if you wanted to solve, let's say 13x equals 6 mod 51. You could keep adding 51 to the right side until you get a multiple of 13. You would get 57, 108, 159, 210, 261, 312, and 312 is the first of these that is divisible by 13. This works, but it is really too much work. Instead, we could convert back to a Diophantine equation. 13x equals 6 plus 51k. That's the same statement, but written in terms of a Diophantine equation. Now solve this like we have done so in previous videos. Write it as a congruence modulo 13, which says that 0 equals 6 plus 51k mod 13. And we can reduce this. We can. This means that minus 12k, if we put it on the left-hand side, equals 6 mod 13. And again, we're reducing mod 13, which says, I'm going to give myself a little bit more room. That means that 2k equals negative 1 mod 13. We divide both sides by 6, negative 6, excuse me. And so 2k equals 12 if we add 13 on the right side. Which means that k equals 6. Because 2 and 13 have are relatively prime, we can divide both sides by 2. Which means that k equals 6 plus 13i. Or, yeah. Now, we can go back and figure out what x is. This means that, again, 13x equals 6 plus 51k. But we know what k is. It's 6 plus 13i. Which means that x equals, we divide everything by 13 and reduce, we get 24 plus 51j. Sorry, I. I'm using I. Of course, you could do this switching back and forth between congruences and Diophantine equations as many times as you like. If you only use this technique, you would essentially replicate the Euclidean algorithm, a more standard way to solve Diophantine equations, specifically the extended Euclidean algorithm. Anyways, thanks everyone, and I'll see you in the next video.